name is Anne-Marie Mouchard, and this is my Physics Lab 3. The objective of this lab was to determine the magnetic dipole moment of a bar magnet and distance dependence using experimental data, as well as create a computational model that visualizes the magnetic field around a bar magnet. We apply the magnetic field formulas for both on-axis and off-axis distances in this lab. The concepts used in this lab are that magnets behave as dipoles. If you look at the B fields, it goes into the negative or south side and comes out of the positive or north side. So the magnetic dipole moment points from negative to positive, in this case from south to north. We can see that they're drawn into the negative side and pushed out of the positive side. Superposition is also used in this, as we find the net field by adding all the individual vector B fields. The magnetic field equation is also used. Magnetic field is inversely proportional to the distance cubed. The standard equation is shown, as well as the special equations for on-axis and being perpendicular to axis locations. You notice that the perpendicular locations magnetic field is half the magnitude of an on-axis magnetic field. So to do this lab, I first downloaded the magnetometer app on my phone, and then I determined the direction of magnetic north by laying my phone flat on a table and rotating till the x component was 0. I then placed a meter stick in the orthogonal direction to determine the north, and I located the magnetometer chip on my phone by following the instructions as shown in the picture. For the on-axis calculation, I found a distance along the ruler that created a magnetic field of 20 microteslas, and then I repeated this 2 more times so that the distance values could be averaged for accuracy. I repeated the previous 2 steps, but for different magnetic field magnitudes of 70, 120, 170, and 220 microteslas, and then recorded the distances for each magnetic field measurement. To find the off-axis data, I first found the distance d perpendicular so that the net magnetic field had a magnitude of 200 microteslas. I then recorded the y component of the Earth's magnetic field using the magnetometer app. Finally, I added a second ruler perpendicular to the first one and moved my phone along it of a d distance perpendicular. That was found in the first step, and then I determined the vector magnetic field at this location. So my observations were that the x component of the magnetic field increased as the magnetometer moved closer to the magnet, and when the magnetometer was far from the magnet, the x direction of the magnetic field was equal to 0. The magnetic component due to Earth must be subtracted from the y component of the magnetic field and the y component only, since the Earth only has a magnetic field in the y direction, and that the magnetometer was sensitive to surrounding materials such as electronics or metals, so I cleared my workspace of them. So this shows my on-axis data. You can see the distances and the averages for them, as well as a graph. I used a natural log graph because I knew that it wouldn't be a linear relationship, so the natural log made for an easier regression. And this is the off-axis data. We can see the x components and the y components and the z components, and that the y component had to be corrected by subtracting Earth's magnetic field. So to find the distance dependence, I rearranged the b bar equals kr to the n by taking the natural log, and I noticed that in this case n would be the slope. And going back to the previous equation, n had a slope of negative 3.03, which is very close to the expected value of negative 3. I then also realized that the natural log of k was the y-intercept, so to find k, I simply did e to it. And then I rearranged the on-axis magnetic field calculations to solve for mu, and found that mu was 2.56. And this is my computational model. I created constants for mu mag and found the dipole moment, as well as arrows for both on-axis and perpendicular calculations to show the direction of the magnetic field. I found that for the 45-degree one, that the x component was 6.64 times 10 to the negative 6, and the y was 1.99 times 10 to the negative 5th, and that the experimental values for both of these were both greater than the computational model. If I hadn't oriented the experiment to compensate for the magnetic north, the x component would not be 0 at the orientation, and the x component would be greater than or less than the theoretical value. And if I had used two magnets, the value and magnitude of the magnetic field would double.